You probably don't think about cadmium much, maybe you never even heard of it, but this shiny silver metal is hiding in more places than you'd expect. It's in some of the batteries we use, the paints on old toys, the plastic in old gadgets, and even tiny amounts in the food that we eat. Sounds harmless, right? After all, it's just a metal. But here's the thing, cadmium is no ordinary element. It's toxic, and not just a little bit. This stuff builds up in our bodies and sticks around for years. It damages organs, weakens bones, and has been linked to cancer. And once it's in the environment, it doesn't go away. So how did something so dangerous end up all around us? Welcome to Cube Chemistry, where we'll discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll in the post section of the channel for next week. Now, even though you guys refuse to choose zinc, cadmium is so close to zinc that we will be discussing some parts of zinc today anyway. Now, what if I told you that the element in this cube looks a lot like zinc? It does really. I compared both cubes and the metals inside are rather similar. But still we have to wait for that comparison, as this week you chose the element cadmium. The element literally in the same group as zinc, that sits under zinc in the periodic table. So what I got here is a silvery gray metal, and I am glad that it is inside a cube again, because boy howdy is this element toxic. And that brings us to the segment, Can You Lick It? Well, in this case we can see that in the periodic licking table that it is a really bad idea. It's marked red, which means please do not do that. I've seen many comments where people are stating, well, you can at least lick it once. But in this case, there is a chance you'll get seriously ill even when you lick it once, which we will discuss later in the episode. Now, if you would like to own your own material that is already banned for use in the EU, for instance, make sure to click on the link in the description, use the promo code, get a 10% discount, and you will be also helping out our channel. The story of cadmium begins in the early 19th century. In 1817, a German chemist named Friedrich Strohmayer made a surprising discovery while inspecting samples of zinc compounds sold in pharmacies. At the time, zinc oxide was used as a medical ingredient, but Strohmayer noticed that some zinc carbonate samples, also known as calamine, turned yellow when heated, which pure zinc carbonate should not do. Suspecting an impurity, he investigated further and managed to isolate a new metal with a bluish-silvery color. Around the same time, another chemist named Carl Samuel Leberecht Hermann independently found the same mysterious substance in zinc oxide. This new element was eventually recognized and named cadmium. The name cadmium has its roots in antiquity. It comes from the Latin word cadmia, which was the old name for the mineral calamine, zinc carbonate. The term cadmia itself was derived from the Greek word kadmeia, meaning Theban earth, named after Cadmus, the mythological founder of the city of Thebes. The mineral has been associated with the legend of Cadmus, and because the newly discovered metal was found within calamine ore, Strohmayer chose to name it after the ore. In essence, cadmium means the metal from calamine. Early on, cadmium's rarity kept it out of widespread use. However, scientists and industrialists soon found particular niches for this element, setting the stage for greater production and use in the 20th century. Physically, cadmium is a metal that is nearly as soft as tin. If you were to hold a piece of cadmium, like outside of this cube, it would feel somewhat heavy. It's denser than zinc. But you could scratch it with a knife or even bend it with pliers. When bent, cadmium, like tin, emits a faint crackling or popping sound, sometimes called a tin cry. It has a relatively low melting point of about 321 degrees Celsius or 610 degrees Fahrenheit, which means it melts at a much lower temperature than many common metals like iron or copper. This low melting point is one reason cadmium has been useful in certain specialized alloys that need to melt easily. Cadmium can also be polished to a high shine, taking on a lustrous silvery appearance when freshly cleaned. Now, one notable property of cadmium is its resistance to corrosion. Unlike iron, which rusts quickly, cadmium does not oxidize, tarnish rapidly in air. In dry air, cadmium's surface can remain bright and untarnished. In moist air, it slowly forms a thin coat of cadmium oxide that actually protects the metal underneath from further corrosion. Cadmium is not a metal that reacts vigorously in everyday conditions. It doesn't react with water, it isn't flammable in a solid form, and it slowly dissolves in strong acid but not in weak ones. If heated on a flame, cadmium will burn with a red-orange flame, forming cadmium oxide fumes. Now, chemically, cadmium behaves a lot like its neighbor zinc, but it also has some similarities to mercury. It typically prefers to exist in compounds in the +2 oxidation state, meaning it commonly forms ions with a 2+ charge. Cadmium compounds can be quite colorful. For example, cadmium sulfide is bright yellow and cadmium selenide is red. These vibrant colors have been used as pigments. Cadmium is categorized as a heavy metal, and like many heavy metals, its chemical compounds are often toxic. It has no known necessary role in the human body, unlike some other metals such as iron or zinc, which we need in tiny amounts. Cadmium appears to be purely harmful to living organisms. Cadmium is fortunately quite rare in the Earth's crust. It's estimated to be present at about 0.1 to 0.2 parts per million in crustal rocks. In other words, if you had a ton of typical rock from the Earth's crust, you'd find only a few tenths of grams of cadmium in it on average. Because of this low abundance, there are no cadmium mines in the traditional sense. You can't go somewhere and dig out cadmium ore as you would iron or gold ore. Instead, cadmium ore is usually found scattered as a minor ingredient in ores or other metals. The primary source of cadmium is zinc ore. The most common zinc ore mineral is sphalerite, which is basically zinc sulfide. Cadmium often sneaks into the crystal structure of sphalerite in small amounts, because chemically it's quite similar to zinc. Typically, sphalerite ores contain about 0.1 to 0.3% cadmium by weight. Now, this means that for every 1,000 kilograms of zinc ore, there might be 1 to 3 kilograms of cadmium mixed in. Not much, but enough that it can be extracted as a byproduct. Cadmium can also be found in small quantities in some lead and copper ores. One mineral, greenockite, cadmium sulfide, is a cadmium-containing mineral that occasionally forms coatings on zinc ores, but you rarely find greenockite in large concentrates on its own. So how do we actually get cadmium metal out of these ores? The production of cadmium is almost always tied to the production of zinc. When zinc sulfide ore is processed, the first step is actually to roast the ore in air. Roasting in this case means heating it strongly in the presence of oxygen. This converts zinc sulfide into zinc oxide, while releasing sulfur as sulfur dioxide gas. During this roasting process, cadmium impurities in the ore don't just vanish, they also react and form cadmium oxide. Cadmium oxide, unlike zinc oxide, will not stay put in the roaster. It tends to volatilize, turn into vapor or smoke, because cadmium compounds vaporize at relatively low temperatures. The cadmium ends up in the flue dust, the fine airborne particles in the roasting furnace exhaust. Now, the next steps depend on the method used to refine zinc. If zinc is being refined by the traditional smelting method, using heat and carbon to reduce zinc oxide to metal, the cadmium often comes off as a vapor during smelting and is captured separately. One common way is to isolate it to collect the cadmium-rich fumes and then heat them in a vacuum distillation chamber. Cadmium has a lower boiling point than many other metals, so it can be distilled out and condensed into nearly pure cadmium metal. If the zinc is being produced by an electrolytic process, dissolving the zinc oxide in an acid and electroplating zinc out of the solution, then cadmium usually stays in the acidic solution after zinc is deposited. By treating that solution, cadmium can be precipitated out, often as cadmium sulfate or other cadmium salts, and then processed to metal. Now, in either case, the key idea is that cadmium piggybacks on zinc production. Apart from zinc refining, cadmium is also obtained from the process of lead and copper ores. though in smaller quantities. If lead or copper ore has enough cadmium content, the smelting process for those metals can be tweaked to recover cadmium as well. Additionally, recycling has become a source of cadmium. For example, used nickel-cadmium batteries can be collected and processed to extract cadmium for reuse. And scrap metal from electroplating operations can likewise yield some cadmium. In terms of geography, cadmium production tends to occur in the same countries that have large zinc smelting industries. Historically, Germany was an early leader in cadmium production as it industrialized and had zinc mines. Now, by the late 20th century and the early 21st century, countries such as China, South Korea, Japan, Canada, and Kazakhstan have been among the top producers of cadmium because they are big players in the zinc mining and refining. Essentially, where zinc goes, cadmium follows. Now, it is worth noting that cadmium doesn't just stay confined in ore rocks. It can also find its way into other natural resources. For instance, certain phosphate rocks used to make phosphate fertilizers contain cadmium as an impurity. Now, when those rocks are made into fertilizer, the cadmium is spread on farm fields, gradually accumulating in the soil. Coal is another unexpected source. Coal can contain trace cadmium, and when it's burned into power plants, the cadmium can go up the smokestack and end up in the ash or emitted into the air. Volcanic activity can also release cadmium from the deep earth as well, spreading it through the air as a compound of volcanic dust and gases. In short, cadmium is widespread in very low concentrations and usually only becomes concentrated to problematic levels through human activities like mining, refining, and burning of fuels. Now, despite its toxicity, cadmium became highly valued in a variety of applications throughout the 20th century. Its unique properties, such as resistance to corrosion, ability to impart bright colors in compounds, and electrochemical traits, made it useful in specific roles. One of the earliest widespread uses of cadmium was in electroplating other metals. Electroplating is a process where a thin layer of one metal is deposited on another metal to protect it or improve its appearance. Cadmium plating of steel iron, copper, brass, and other alloys became popular because cadmium is excellent at preventing corrosion. A coat of cadmium on a steel compound will shield it from rusting, even in harsh environments. Cadmium-plated steel is especially resistant to salt water and to alkaline environments, which made it ideal for marine hardware, aerospace components, and military equipment. For example, aircraft parts and fasteners were often cadmium-plated to ensure they wouldn't corrode under tough conditions. Cadmium's ability to form brightly colored compounds made it a star in the world's pigments. The classic examples are cadmium yellow, cadmium sulfide, and cadmium red, cadmium selenide, often mixed with cadmium sulfide for orange shades. These pigments were first introduced in the 19th century and gained popularity among artists and manufacturers for their vibrant hues and good stability. Cadmium yellow, in particular, provided a rich lemon to golden yellow that was much more light-fast and stable than earlier yellow pigment. Some of the great painters of the late 19th century and the early 20th century, like Claude Monet and Vincent van Gogh, are known to have used cadmium-based pigments to achieve certain bright yellows and oranges in their artworks. In addition to artist paints, cadmium pigments have been used in industrial paints, plastic, ceramics, and glass to impart bright and long-lasting colors. For instance, the bright red or yellow of certain plastic objects or ceramics often came from cadmium compounds in the past. Perhaps the most significant use of cadmium in the latter half of the 20th century was in rechargeable batteries, specifically nickel-cadmium batteries, commonly abbreviated as NiCad batteries. These batteries use cadmium in the metallic form as a negative electrode, anode, and nickel oxide hydroxide as a positive electrode, the cathode, with a potassium hydroxide alkaline electrode. Nickel-cadmium batteries became widely used in portable electronics, cordless, powerless tools, flashlights, and even as backup power supplies and in aviation. They were popular because they were robust. Nickel-cadmium batteries can be recharged hundreds of times, deliver high current, and are relatively tolerant of abuse, like overcharging or cold temperatures, compared to earlier battery types. In fact, during the 1980s and the 1990s, nickel-cadmium batteries were the go-to rechargeable batteries for things like cordless telephones, RC toys, and early cell phones. If you've ever used the rechargeable AA batteries in the 90s, it was likely nickel-cadmium. Cadmium's role in the battery is crucial for the electrochemistry that allows these cells to be rechargeable and stable. However, nickel-cadmium batteries have a downside. Beyond just cadmium's toxicity, if disposed improperly, they also suffered from what is called a memory effect. If you didn't discharge them fully before recharging, they could lose capacity over time. Over the last couple of decades, nickel metal hydride and lithium-ion batteries have largely taken over the roles that nickel-cadmium batteries used to play. These newer chemistries do not contain cadmium and can often store more energy. As a result, the proportion of cadmium used in batteries have been declining in consumer products. But nickel-cadmium batteries are not gone. They are still used in certain applications. For example, some aviation batteries, emergency lighting, and other niche uses continue to use nickel-cadmium batteries because of their reliability in specific conditions. And in some regions of the world, cheaper nickel-cadmium rechargeable batteries are still in use for consumer electronics. Cadmium is also used as an ingredient in various alloys, mixtures of metals, to impart special properties. One common theme is low melting alloys. Because cadmium melts at a low temperature, if you mix it with other low melting metals like bismuth, lead, tin, or indium, you can create alloys that melt at an extremely low temperature, sometimes even below the boiling point of water. Now, these alloys are used for special purposes like automatic sprinkler systems, which need a metal fuse that melts in a fire to trigger water flow, safety devices, or special soldering brazing applications. A classic example is Wood's metal, which is an alloy of bismuth, lead, tin, and cadmium that melts at around 70 degrees Celsius or 158 degrees Fahrenheit. Cadmium's presence helps lower that melting point. Starting around the mid-20th century, cadmium compounds like cadmium stearate or cadmium laurate were used as stabilizers in polyvinyl chloride PVC plastic. PVC, which is a common rigid plastic used for pipes, vinyl, siding, and countless other products, can degrade when exposed to heat and light unless stabilizers are added. Cadmium compounds were very effective at improving the heat and weather resistance of PVC, preventing it from breaking down and discoloring. For a time, many PVC products, including some older plastic toys, plumbing, and vinyl records, contained small amounts of cadmium. However, the awareness of cadmium's toxicity led to a push to eliminate cadmium stabilizers. Today, cadmium-based stabilizers have been completely replaced in most countries by alternatives like barium zinc, calcium zinc, or organotin compounds. Cadmium has found its way into various electronic applications over the years. In the era of cathode ray tube CRT televisions, the old bulky TVs and monitors, cadmium was used in phosphors. Especially cadmium sulfide was used in some black and white TV phosphor coatings. And cadmium compounds were used in some of the colored phosphors for color TVs. Older photoelectric cells and light sensors sometimes used cadmium compounds like cadmium sulfide. For example, the light-sensitive resistor in street lights' dusk-to-dawn switch was often a cadmium sulfide cell that changes resistance with light. Cadmium's applications in electronics have evolved with technology. In recent time, cadmium telluride has become important as a semiconductor for solar panels. Cadmium telluride solar cells are a type of thin film photovoltaic technology that can convert sunlight to electricity. They have been used in large solar panel farms because they are cheaper to produce than traditional silicon-based panels and perform well in high-temperature environments. One of the world's largest energy companies built its business on cadmium telluride panels. The irony here is that cadmium, a toxic metal, is being used to produce green energy. Another cutting-edge use of cadmium is in quantum dots, which are extremely tiny semiconductor particles that can emit very pure colors of light. Some of the highest performance quantum dots for display technologies, like those used in certain high-end QLED television screens, are based on cadmium selenide. These cadmium-based quantum dots can produce intensely saturated reds and greens, enabling TVs to have a wider color range. However, because of regulations and public perception, many manufacturers are racing to develop cadmium-free quantum dots using other materials such as indium phosphide, even if the currently sacrifices a bit of color performance. So cadmium is holding on in some of the newest TV tech, but its grip may be loosening as alternatives improve. There are other niche uses of cadmium as well. Helium-cadmium lasers produce certain UV and blue laser lines used in some scientific instrument and holography. Cadmium-based compounds are being researched for use in certain cancer treatments, though their toxicity is a limiting factor. And cadmium is used in laboratory research, for instance, as a reagent to help understand calcium channels in biology. Cadmium can block biological calcium channels in experiments. Cadmium is a highly toxic metal, and its toxicity was not fully appreciated until the mid-20th century, when industrial use had already grown. Unlike some hazards that cause immediate reactions, cadmium is often a silent poison. It can accumulate in the body over time and cause chronic effects that sneak up on people. One of the most dangerous features of cadmium is that the human body has a very hard time expelling it. If cadmium enters your body, whether through inhalation or ingestion, a significant portion of it will be retained. Our bodies have a protein called metallothionein that can bind cadmium to reduce its damage, and we slowly excrete very small amounts. But these defenses are easily overwhelmed by higher exposures. Cadmium's biological half-life, the time for half of it to leave the body, is on the order of decades. Estimates range from 10 to 30 years. That means that if you get exposed to cadmium regularly, it keeps building up, especially in organs like the kidneys and the liver. Over years or decades, even low-level exposures can reach a tipping point where the amount of cadmiums in your organs is enough to cause damage. Cadmium and its compounds are recognized as human carcinogens by the International Agency for Research on Cancer and other health bodies. The most well-established link is between cadmium and inhalation and lung cancer. Workers exposed to cadmium fumes or dust have higher rates of lung cancer. There are also studies that suggest cadmium exposure through diet might be associated with increased risk of cancers, such as kidney cancer or prostate cancer, and some links to breast or endometrial cancer have been observed. Cadmium is thought to possibly act as an endocrine disruptor, meaning it can interfere with hormone systems. For example, cadmium can mimic estrogen in certain biological systems, which is a suspected mechanism for how it might influence hormone-related cancers. While the exact pathways are still being researched, the bottom line is that cadmium is not just a poison, but also potentially carcinogenic, even at relatively low chronic exposure levels. One classic example of environmental cadmium uptake is the discovery of cadmium in cocoa beans and consequentially in chocolate. Cocoa plants can absorb cadmium from soil, and this is particularly a concern in some regions with volcanic soils or areas fertilized with high phosphate cadmium-containing fertilizers. In recent years, tests on dark chocolate have shown measurable cadmium levels, prompting some governments to consider guidelines or warnings, especially since children may consume cocoa products. It's a reminder that cadmium pollution doesn't stay confined to a factory. It can end up in most unexpected places. Another major exposure route is cigarette smoke. Tobacco plants are particularly adept at absorbing cadmium from soil. Cadmium concentrates in tobacco leaves, so when smokers inhale cigarette smoke, they are also inhaling cadmium vapor and particles. It is estimated that about 1 to 2 micrograms of cadmium are in each cigarette, and up to half of that can be absorbed by the smoker's lungs. Smokers tend to have significantly higher cadmium levels in their bodies than non-smokers, often on the order of 4 to 5 times higher in blood cadmium levels. The difference is so marked that cadmium levels can be used as a biomarker to indicate if somebody is or was a heavy smoker. This adds to the list of smoking's harms. Lung and kidney damage from cadmium is one of the lesser known, but very real consequences of long-term smoking. Non-smokers mainly get cadmium from food, but those living in polluted areas might also inhale from air, industrial emissions, combustion engines, etc. Due to cadmium's dangers, very strict safety limits has been set in workplaces. In many countries, workers are not supposed to breathe air containing more than a few grams of cadmium per cubic meter on average. Public health guidelines also set tolerable daily or weekly intake limits for cadmium from food. For example, the European Food and Safety Authority has recommended a tolerable weekly intake on the order of 2.5 micrograms per kilogram of body weight. These guidelines are meant to ensure that even over a lifetime, cadmium accumulation stays below levels thought to cause kidney damage. However, these are cautious estimates. Some research indicates even lower levels over time might contribute to subtle health effects. Cadmium's toxicity has led to high-profile product recalls and scandals. In 2010, it was discovered that some inexpensive children's jewelry imported into the US, for instance, charm bracelets and necklaces, contained very high levels of cadmium. Manufacturers had apparently turned to cadmium as a substitute for lead, after lead in children's jewelry was banned. Unscrupulous suppliers used cadmium, which is just as bad or worse. Children sucking or biting on such jewelry could be poisoned. This prompted regulation action and recalls. For example, a major retail chain had to pull cadmium-tainted jewelry off the shelves. As the harmful effects of cadmium became clear, governments and international bodies began to take action to limit cadmium's exposure. Over the past few decades, there have been increasing restrictions on cadmium use, especially in consumer products. In workplaces, strict limits govern cadmium exposure. For instance, occupational safety agencies like OSHA in the United States set permissible exposure limits for cadmium in air, often as low as 5 micrograms per cubic meter over an 8-hour workday. Several jurisdictions have essentially banned cadmium in many types of consumer goods. The European Union has been a leader in this regard. The EU's Restriction of Hazardous Substances Directive lists cadmium as one of the substances that cannot be used above a very tiny threshold in electronics and electrical equipment. Now, given all these steps, one might think, isn't cadmium already basically banned? The answer is, in some places and some uses, yes, but not universally for all purposes. Cadmium's use has been declining sharply in many countries, but it has not been completely eliminated worldwide. There are countries with less restricted enforcement where cadmium is still used in cheap consumer goods like pigments, in toys or plastics, or in jewelry, as we saw. Now, the reason many scientists and policymakers advocate for a global ban for most purposes is that we now have sufficient knowledge and alternatives for the majority of cadmium's uses. A useful parallel is lead. Lead was once freely used in gasoline, paints, and many products worldwide. Once its harm was undeniable, countries agreed through various initiatives to eliminate lead in those everyday uses. And today, leaded gasoline is gone almost everywhere. And lead in paint is banned in almost all countries, with a few exceptions that are being addressed. The good news in the cadmium story is that for almost every major use of cadmium, alternatives exist. Let's go through a few of them where that isn't the case. Now, manufacturers might do cadmium plating because switching processes has an upfront cost. These are economic and transitional challenges, not scientific impossibilities. Now, in highly specialized scientific research, cadmium may occasionally be necessary. Certain experiments require cadmium-based detector or cadmium compound as a reagent, but these uses are extremely small scale and usually very contained. Lab safety protocols handle them. Perhaps the hardest place to replace cadmium completely is historical applications that are still in use, like older aircraft or equipment that have cadmium parts in them. Those parts will need to be maintained or replaced with cadmium-coated spares until the equipment is retired or retrofitted. This means that even if we ban new uses, we have to manage legacy cadmium safely. Another area might be the arts world's preference for cadmium pigments. While alternatives exist, some artists feel there is no exact replacement for richness of cadmium red or yellow. Cadmium's journey over the past 200 years is a cautionary tale of a double-edged sword. On one side, it has offered useful properties that spurred technology advances: brighter paints, long-lasting batteries, rust-proof coatings, and cheap solar cells. On the other side, it has inflicted grave harm, poisoned workers, polluted rivers and rice fields, weakened bones and kidneys, and caused cancer and deaths. It is a metal that helped industrial progress, but at a cost that was not understood until far too late. Today we know the truth about cadmium. It is a toxic pollutant that lingers in our bodies and ecosystems for decades. We also know that its usefulness, while real, is mostly something we can replicate or replace with safer methods. Now, if you think we missed anything, let us know in the comments, and if you want to know about another toxic element, watch the video about arsenic next.